Okay, we have a lot to discuss today. So, last class we talked about how to inject a share-code in the address space. We talked about multiple approaches to do that. You can put that in environment variable. You can put share-code in binary argument, or you can just put that on other places on stack, depending on the vulnerability of the code. Then you overwrite the return address of that vulnerable function. So when that vulnerable function returns, it doesn't return to whatever function calls it, instead of return to your share code. Then your share code, since you inject that, you can do whatever you want. It's just a byte sequence of instructions. You can generate that byte sequence by writing assembly, compile it, then get the bytes. So today, we will talk about what if you cannot overwrite the return address. You can only overwrite the saved EBP or saved RBP on the stack. So you are overwriting fewer bytes, but still you can get full control of this. This is a little bit counterintuitive at the very beginning. The return address one is very natural. But this one is a little bit counterintuitive, but the way we'll see how it works. We're going to use one share code, which is this long share code, which is much better since we only need to make two system calls. This is not the simplest form of share code you can use. In the share code workshop in 2 weeks, you will design even simpler share code. So the attack we are doing today is basically overwriting the frame pointer. So this is also called the frame pointer attack. The frame pointer, obviously, is not a code pointer. That return address, since it's an address, it points to somewhere. It's pointing to code. So it's a code pointer. The saved EBP, saved RBP doesn't point to code, but it's pointing to someplace, pointing to the previous functions saved EBP actually. So this is a code pointer. And by overwriting that one, we can change the upper level function's return address. Let's say we have main function calls valfoo. If you overwrite valfoo's return address, when valfoo returns, return to your share code. But if you overwrite valfoo's saved EBP, then valfoo returns, valfoo still returns to whoever calls it, which is a main function. But when main function returns, it will use whatever EBP points to somehow, finding the return address to that, related to that. So you are actually changing the upper level function, the main function's return address, not the valfoo's return address. So let's look at this example. This is overflow 6. I didn't name it overflow return 6 because you are not directly overflowing the return address here. Main function checks whether there are 2 arguments, that's it. Then the command line arguments, the second command line argument is provided as the parameter for valfoo. Okay, so you know the input is command line. In valfoo, C code level, we have a buffer, 4 bytes. We print out for you where the buffer is. Then we do a memory copy from the command line arguments to the buff. We copy 12 bytes here, okay? That's it. And there is no print flag in the address space, which means you need to inject the share code here. So let's take a look at the disassembly here first. So if we disassemble this, we can find the printf. Printf actually tells us where the buffer is, right? No, printf gives us printf print out a string there. So memory copy actually give us the address. The first parameter of memory copy is where our buffer is, and you can say memory copy. There is a push EAX. The EAX is an EBP minus 8. Okay. So at C code level, we ask for 4 bytes. The compiler actually give us 8 bytes for the buffer. The distance between the beginning of the buffer and the saved EBP is 8 bytes. Then we can overwrite 12 bytes, okay? Which means we can overwrite that buffer 8 bytes. Then we can overwrite 4 bytes, which is the what? The saved EBP on stack. And we cannot overwrite the return address, okay? So if we run this program, by the way, there is another tool I want to introduce you guys. Is we have a tool here called checkstack for you. You can run this tool. You have to do files. You have to run this tool. You can run this tool, which tells you what kind of security features this binary has. For example, this one, there's no Canary. Stack execution is disabled. Non-stack execution is disabled, means you can't execute the stack. PIE, position independent code, is enabled. The other security features as well. So if you write a script using Pound tools will also tell you those features as well. So when you hack, if you do not use Pound tools, you can use this to get a basic feeling of what kind of security features are already there. So if we run this program, if we just have a short input, obviously, so this one, I give a very short input here. I only give 8 bytes. But why I still get a segmentation fault? Why I still get a segmentation fault? Close, but not really. So what is a vulnerable function here? Is it string copy? No, we're not using string copy. We're using memory copy. And memory copy is copying 12 bytes. Okay, no matter what, it's copying 12 bytes. It's not string copy at the end of the string. Okay, so which means even if I provide 8 bytes here, then the 9th byte will be 0, like you said. Then there will be another 3 bytes will be copied, which we don't know the value. And those values will be copied into the memory location of saved EBP there. Right? So why does that cause a segmentation fault? Then we can debug this. We can do a GDB of this. Let's set a breakpoint at the vol-foo. That'll be, or maybe I set a breakpoint of the end of vol-foo. Let's set a breakpoint after memory copy. That'll be before memory copy, so you can see the changes there. We set a breakpoint here. Then we run this program. We give it just some random inputs. Not really matter. Cannot insert breakpoint 2. Oh, right now we do not have the runtime address yet. Let's see. Just run this program from beginning. How do I remove a breakpoint? Let's set a breakpoint on main first. Whatever. Then we run this. Cannot insert breakpoint 2. Command to remove breakpoint in GDB. Delete. Okay, just D. Okay. So it should be D2 or? Okay, it works. Now we just run. Now we are in main. Then we keep going we continue to vol-foo. Now we are in vol-foo. Then let's find the runtime address of that. There's a runtime address. B. So we continue again. Now we are at this address of Overflow. We are about to call memory copy, right? We haven't called it yet. So let's examine the stack. So now, where should we examine? We can examine where the buffer is. Okay. So let's do a exam. Let's say 12 bytes. Let's do more. 16 bytes. Hex at where EBP minus 8 is. Okay. So this is what our stack look like right now. We have 8 bytes of zeros. That is where the buffer is, right? Now after that, we have 4 bytes. What are those 4 bytes? This is low address, this is high address. What are those 4 bytes? The saved EBP, right? The saved EBP. And look at this address. This is a pointer. This is FFFF. So this is still stack. And this address is higher than the current address, okay? So this one points to the previous functions saved EBP, okay? And this one is there because at the beginning of the function, we have a push EBP instruction there, right? Then after that, we have 4 bytes. What is this? 56, 55, 62, 5D. What's that? That's a return address. Where is this one? Where is this address? EBP plus 4? That's a location of that. I mean, where does this point to? Exactly, somewhere in the main function. Actually, it will be the function, the address after call Overflow, right? We can check that. We can disassemble the main function, and you can say there is a call Overflow, and after that, the address is 62 5D, right? Exactly the same here, 62 5D. Okay. Now, we're not going to step into memory copy. We know memory copy will copy 12 bytes. Okay, we don't care how it does that. So we will just do a next. We'll do an N here. Next instruction. We do not step into that. Then we do that. We check again. So right now, we are at this address. We just returned from memory copy. Memory copy is another function. A lot of instructions there. We didn't go into that. We're here. So let's check the stack again. We use the same command to check the stack again. And the stack is changed. Right? We copied. I put some random input, which I do not remember what they are, but we overwrite 12 bytes here. Okay? 8 bytes of buffer, another 4 bytes of saved EBP. We didn't touch the return address. Okay. So now we keep going. We are here. So the next instruction to execute is AND this number to ESP. We do an NI to go one more step. Do another NI to move 0 to EAX. So here we're using AT&T syntax. Sorry about that. Now we're moving EBP minus 4, whatever, to EBX. Probably doesn't really matter what we're doing here. So now we are at the leave. Okay. Remember what is leave? The leave instruction is basically equivalent to 2 instructions. Move EBP to ESP, then pop EBP, right? So after this, we're going to put EBP into ESP. So let's do a print EBP. EBP has this value. Print ESP as well. ESP has this value. Then after we do this, both EBP and ESP will be changed. They have a new value. And EBP we'll have the value we put on set. Okay. Now the next instruction to execute is return. Okay. Return will just pop whatever ESP points to the register EIP, right? So what ESP points to right now? What? No, the return address. And we didn't overwrite that, right? So this return here will not return to our shellcode. Okay? We do not even have shellcode, but it's not going to return to wherever we want to return because we didn't overwrite that. So we do an NI again. So we are back at the main function now. We're here, right? Do we have a crash? So far, we don't have a crash. Right? Even if we override the saved EBP, after we return, we don't have a crash. Okay. But if we keep executing from here, now we're going to the leave instruction again. Okay. This leave instruction will crash the program. Because this leave instruction will refer to the saved EBP. The saved EBP was supposed to be somewhere on the stack. But now, we overwrite that address. Now it's pointed to somewhere we don't know. It's going to dereference that. And that will trigger, we do an NI again, we get them a segmentation fault. Because we dereference the address there, which probably doesn't exist. Okay. So, that's how it works here. So now, at least we know we can crash the program. We don't know how to exploit this yet, but at least we know there is a bug here. Okay, so a little bit of animation here. We have buffer 8 bytes, and we have the saved EBP. Let's say we overwrite it with 4 8s. Then after the return, we will return to the main function, and the main function has an add 4 bytes to ESP. So ESP will point to somewhere here. Then move 0 to EAX, which doesn't really matter here. Then we have another leave function, leave instruction in the main function, which is equivalent to move EBP to ESP and pop EBP. Okay, let's see what we have here. We move EBP to ESP. Then let's see, where are we? Animation here. So EBP at this point has a value 4 8s because we already have a pop there. Okay. Then after that, ESP will get its value from EBP. So ESP will also have 4 8s, right? Okay. Then we're going to pop EBP. Pop EBP means whatever ESP points to will be dereferenced and put into EBP. And ESP points to 4 8s. Okay? So we're going to dereference that in the memory, and obviously that memory doesn't exist. That's why we have a segmentation fault. Okay. Because it's a pop, ESP will also be increment for 4 bytes. So AAA here becomes AAAE. Then EBP will get whatever the memory address AAA has. Probably that address is not mapped. That's why we get a segmentation fault. But after that, we will return. So return will use whatever ESP points to, right? So ESP now points to AAAE. And return will dereference that address AAAE and try to return to whatever that address points to. Make sense? Of course, in the demo I just showed you, we didn't even reach here. Okay? We get a segmentation fault at this line of code. We didn't have a chance to execute this line of code. So now you understand how we can change the EIP here. So here we have another opportunity to change EIP because of this return. Okay. But this is a return of the main function, not the return of the val. Right? So how do we exploit this? Can we exploit this?
We can point the EIP towards shellcode. Right.
Eventually, the goal is to point to the EIP to the shellcode here. Yeah, because you do not have a chance to do that for at the return of Overflow. You have a chance here, right? And how do you do that?
So is the tricky part where we're putting the shellcode, or is it
No.
we just going to
The tricky part is probably where you put the shellcode, because shellcode, what we learned from last class, we can put it just in environment variable, right? Or we put it in command line arguments. That's the easy part. The hard part is you can only overwrite technically 4 bytes. There are 8 bytes of garbage. No matter what you overwrite, they don't matter, right? What matters is that the saved EBP, that 4 bytes. That is a critical thing. Okay. So how do you cleverly overwrite that?
Wherever we put the shell code,
Okay.
when we call the next instruction, ESP goes.
Okay.
It is loaded with the shell.
Okay. That's the basic idea, but there probably is more complicated than that. Okay. Let's say we can override this EBP, right? Let's say we override it with X. One way we can do this is this is an address. We call it X. Then somewhere we are going to create a fake stack frame for the main function, because this one is supposed to point to the stack frame of the main function, which is supposed to have a higher address than this one, right? But now we are going to override this, so it will not point to the real main function's stack frame. We create a fake one, and the fake stack frame should look like this. It should have the address of the return value, right? This is a return. So technically what matters is 4 bytes. The return address here, but it will point to what? It will also point to the saved EBP, right? The saved EBP of what? Of whatever calls the main function. Okay? The lib say start main function. Do we care about this one? We don't. Okay? Because what we care is we want to exploit this when main function returns. Okay, as long as main function returns to our shellcode, game over, right? So this 4 bytes, we don't care. But the structure will look like this. This pointer points to 4 bytes, and the first 8 bytes. The first 4 bytes can be anything. The second 4 bytes has to be the address of our shellcode. Okay. So this is one way to do that. And the whole thing is 8 bytes. Because the whole thing is 8 bytes, we can put the 8 bytes here, right? And we can put it in other places as well. Let's say we can just put it in anywhere. This is the most easy way. We have a huge, it's not a sled, but it's a huge chunk of memory. We just spray that huge chunk of memory with the address of shellcode. Okay? So whatever X points to, that 4 bytes will not be used. But the next 4 bytes will be used as the address of shellcode, right? So we don't need to know exactly where X points to. Make sense? Okay. However, there's still a problem. What's the problem here? What could happen here? Any problem you can think of? What if you point to the middle of this 4 byte shell code? What will happen? Then you will get half of the shell code and another half, then still 4 bytes, but that will not be shell code's address, right? So which means how many guesses you need to do here? You only need to do 4 guesses, okay? Then it would work, right? So this is an easy way to do that. Of course, because it's technically you only need 8 bytes, you can put the 8 bytes here. So X points to here, 4 bytes of garbage, 4 bytes of shellcode. So technically you can also make the X a little bit 4 bytes lower, right? If you're 4 bytes lower, then X will point to actually here. It's a mistake here. X will point to here, then the shellcode address will be here. Of course, you can also make X point to somewhere 1 byte off each here, because you can overwrite this part. So those are many different ways to exploit this. So let's try this. First, let's get a share code out there. This is our share code. So all bytes. That's it. Let's do 2000. Should be enough. This is a challenge. Okay, we get the share code here. 32 S code. Now we have share code somewhere here, and we have 2000 bytes of knob sled. Give us a lot of flexibilities. Okay. Then let's do the very first approach. This one. We are going to create a fake stack frame here. Okay. How do we do that? Where do we inject this thing? Obviously not the input, because this is only 8 bytes. So where do we inject this? Do we have any code here? No, right? They're all pointers. The data, the address. Where do we inject that?
Can you make an address of like code that like an executable that you wrote?
I don't get what you say.
Like, does it like this example, for example, does not have print flag, right? But we want to print flag, so we can make our own and point it to that.
We already have share code. The share code will print the flag for us.
Oh, okay.
Now we just need a memory region. We need to spray that region with the address of the share code. That's it. Okay. So how do we find the address for this? How do we do that?
Environment variable.
Yes, we can also use environment variable, right? Okay. So let's say this address we already know. Then we also know that we have 2000 bytes of knob sled. So we add this maybe a little bit bigger. So let's create another environment variable. Let's call it. Let's just call it A. Doesn't really matter what we call it. So that we don't need the knob sled. We don't need. Oops. We don't need any of those. What we need here is just the address of the share code. Okay. So which will be something bigger than this. Right? So let's just guess a value there. FF. This one we have D6, C5. Now we'll just do maybe D6, FF. That's it. Okay. So how many of this we want? Maybe 300. We also have 300 of this. Okay. Now let's get those address again. This one didn't change, which is good. Okay, there's another address. So we have two environment variables. One is called A, another one is called S code, share code. A is basically a memory region sprayed with the address of share code. That's it. Now we just need to get the A's address to the program we're running. So the program we're hacking is this one. So we just do Python 2. So what do we have here? First, we have we have 8 bytes of garbage, right? So we're overriding the save the EBP. Okay. So 8 bytes of garbage plus save the EBP, which should be where A is. And we have like 300 of them. So we have a kind of buffer there. Let's say, so this one is CC1D. Then let's just do CCFF, maybe like that. Okay. Let's try if it works. It doesn't work. But like we said, there are at least 4 addresses we need to guess. Right? 4 consecutive addresses we need to get. Then let's do FE, that work. D, works. Okay. C, doesn't work. Okay. So we only need to guess 4 times. We don't know exactly where that spread saved the EBP string stack area is. We don't know exactly where it is. We have a rough idea where it is. We don't know exactly where shellcode is. We have a rough idea where it is. That's it. Then we guess the 4 types, and one of them we got the shellcode. We got the flag because the main function eventually returns to our shellcode. Okay. That makes sense? We need to debug this to understand this. Okay, we can debug a little bit. Let's debug this. We have shellcode already there. The address may be changed when we debug, but it doesn't matter that much. I don't remember. Do we use the same syntax when we debug this? Let's set a breakpoint first. Set a breakpoint at Overflow first. Then run this. This is still correct syntax. Okay. So now we are in Overflow. Overflow, we still set a breakpoint here. Execute this. Let's just do one more step. After we come back, then we examine the stack. Exam what 16 bytes hex from where EBP minus 8 is. Okay. Okay, let's see what we have. We have 4 A's, 8 A's as input, fill the 8 bytes of buffer. Then we have this address as our fake, where our fake stack frame is, FF, CC, FC, right? So let's examine that location. Say if X is exam, then after X, you specify how many bytes you want to exam and their type, and you want to say hex or decimal. So let's say we exam 24 bytes, 24 items, X here at which address? I think it's W for white at the address FF, CC, FC. Okay. Oh, that's exactly what we want, right? No, this one is different. It should be FFF D6FF. It should be FFF FFD6. Now we are reading FFD6. Okay, so this probably is a little different from outside of GDB. But that is the address we read. But this is obviously what we put there. Okay. But from here, let's keep doing this. Now we are at after memory copy. We keep going. We are going to return at 6 to 30. Okay. Now we are going to return to main function. Now we are in main function. No crash yet. No flag yet. Now we are going for main function to return. The leave here, let's say. So now, what is the value? Because now we are at here, return. So we're going to return whatever ESP points to, right? So then let's examine what ESP points to. ESP. Okay, ESP points to this address, FFD6FF, which is wrong. So we're going to get a segmentation fault, I believe. Let's do this again. Is that right? That is the right address? Oh, I'm not sure. Okay. Let's do a EIP here. If you want to check if that's a share-code, you can do I here. So the X command tells that GDB to examine a memory, and the memory location is where EIP points to. Then we are going to examine 24 instructions. I here means instruction. So let's take a look if that is our instruction. No, it's not. Okay. Is it? Is that not said? Not sure. Let's just continue. We get a segmentation fault. So that's not the address. So what is the problem here? I think the problem is because of this. That 4 addresses, right? So we were pointing to at the middle of that address. So instead of using C, outside of GDB, we are using C, but inside GDB, the address changed a bit. That's why we need to use E here. Let's run E again. See if it works. We don't have a breakpoint there. Let's skip this one. We go to the main function. Yes, we have a breakpointer. Okay. Breakpoint. Then here we go. Okay, we're in main function. We disassemble main function again. We execute to return 66. And let's examine the return address again. It should be this one. Okay, this now it looks good. Right. FF D6. That looks very high. That looks super high. Huh. What was our address? Probably not that one, but anyway. We do a SI again. We examine if that's our share-code. No, that address is too high. So not that address. So what is our address? Oh, our address probably is 3F. The D6 should be here. I think that makes more sense. D6 should be the 3rd byte. What do we have tried so far? We have tried D6 as a 2nd byte. D6 cannot be the 1st byte, obviously. So it should be I think it should be the 3rd byte. Which means instead of E, I think it should be D. Problem is D. Let's try this again. Continue. Again. The main function. D6. We examine. Try this one. Examine the stack again. Okay. D6 is the 3rd byte. Let's do an NI again. And examine this. Oh, that's good. Okay, that's our NOP. We eventually lead to our share-code. So now I execute. Will I be able to get a flag? Really? Okay, you think we will get a flag. How about you guys? Okay. Why?
Because in DBB, you don't have the privilege.
Yes, that's right. So we will not be able to get the flag here, but you can see we are actually running our share-code. The reason we cannot get our flag is because our GDB is not a pseudo program. It's not a pseudo GDB. So we'll debug a setuid program. That setuid program doesn't really have root privilege. That's why we cannot get a flag. But that is how it works. Obviously, we can use the other 2 approaches. Let's try this one. This one we need to know the exact address of this buffer though. But the program I wrote, the vulnerable program I wrote actually gave you the exact address. Okay. It gives you the exact address. The buffer is at C9A4. Okay. And the buffer will have 8 bytes, right? And that 8 bytes, what do we want to write again? So now we do not have that huge area of share-code addresses. We're going to write the share-code address at that buffer. Multiple ways to do that. Let's use this way. So X, this saved EBP should point to the beginning of the buffer. Then add that 8-byte buffer. We should have 4 bytes of garbage, then 4 bytes of the share code address. That's it. Where's our share code? Share code is somewhere here. So now we have we can put 2 return address there because the first 4 bytes will be considered as garbage anyway. So have D6, say 5, and just go FF. Okay. So we have 2 of those. They will fill the buffer, right? Then what is the after that? What do we put here? 8 bytes of 4 bytes of garbage, 4 bytes of a return address of share code, then another 4 bytes to overwrite the saved EBP, right? So what do we put here? The buffer's address, exactly. We just put the buffer's address there, which is A4, C9, FF. So we can also get the flag. So if we make this address a little bit lower, 3, it won't work. But if I change this to 0, will it work? It works, right? Because now it points to 4 bytes lower than buffer. Then the first 4 bytes of buffer will be considered as a return, not return address, the saved EBP address. So this should also work, right? So this also gives us flag. Yeah.
You explain again why you put the 4 bytes?
That's because so the EBP at this point should point to the stack frame of that function. So it should point to the saved EBP. Okay. And what is higher than saved EBP? The return address, right? Return address will be used by the return instruction at the end. Okay. This one will eventually be popped into EBP. Okay. So EBP will not point to here. So there is a leave instruction to pop this value from stack to EBP. So this is also a pointer. This one actually points to the previous function's stack frame. The previous functions saved EBP, basically. Let's say this function is, this is a main, and this one is a start main, whatever. Then here we have return, we have another saved EBP, and this will be vol-foo. Okay, something between, we don't care. So this saved EBP will point to here. So what we are trying to do is we are overwriting this one, vol-foo's saved EBP. So it doesn't point to here anymore. It's pointing to whatever we want to point, right? But it still should follow this kind of structure. So we are going to create another saved EBP and return address. So this saved EBP will be useful if you are not trying to return at the main function. If you are trying to return at the start main function, then you can do this. But we are trying to return at the end of the main function. So this one doesn't really matter for us. That's why it's garbage. Same as before, last class, you are trying to override this. And you are trying to exploit when vol-foo returns. So you don't care about this. You only care about this. Make sense? Yes. Same thing here. And the first approach we demonstrate is, since this part doesn't really matter what it is, we can also put return address here, right? Then we just have, like almost a megabyte of this, okay? So now this pointer can point to anywhere as long as it's at the beginning of a return address. That's why we tried 4 different addresses. That's it. The same thing works for 64-bit, but you need to try 8 times instead of 4 times. Okay, so let's revisit the conditions we depend on to pull off this attack again. We still need the ability to put shellcode on stack. And we know how to do that, environment variable, command line arguments. We still need the stack to be executable because our shellcode is there. Okay. We still need the ability to overwrite a return address or the ability to overwrite the saved EBP, which eventually leads to the return address, right? And we still somehow need to know the address of the shellcode. Not exactly, but the address. Okay. So that's about the buffer overflow. The next we talk about how do we defeat this and why those defenses are not necessarily good. So there are many different ways to defeat buffer overflow, especially after it was discovered in the 80s. A lot of changes has been made to our hardware, software, compilers, everything. Even today, we're still working on those domains for different architectures, for different compilers. One approach to do that is to fully prevent this. Okay, we call it a direct defense. It can stop this kind of attack. The problem is that usually they are very good in theory, but very expensive in real world. They will work, but they will slow down your computer, your program 3 times, 4 times. That's why no one actually deploys them in real world systems. Then there are some indirect defense. They do not eradicate the problem, but they make the exploit slightly harder. But computational wise, they could be very, very affordable. They only add 1%, 2% of overhead, which most people cannot notice. And those, they are not complicated or perfect in theory, but they are widely deployed in real world. So we're going to go over some of those approaches. The first approach is the base and bound check. This one actually prevents all kinds of buffer overflows. But they are not really deployed. There are some hardware solutions as well, but they're not really deployed. Then there is a stack cookie, or called stack Canary approach. They are indirect defense. They can prevent overwrite of a return address, and they are widely deployed. All your systems you are using, they have this approach. It's very affordable, but it's not necessarily secure. A lot of we actually have a paper published last year talking about for embedded systems. This is not working at all. Then there are data execution prevention because we are injecting shellcode onto the stack. And we talked about this before. There is no legit reasons for us to put code onto the stack. So we just make the stack not executable. That's it. Very simple, right? So the base and bound check is a very simple idea. Let's say we have a pointer. We have a pointer A. Then we create some other pointers for A as well. We have A is compiled into A base. Then there is also a bound. If we do a malloc A, we malloc 500 bytes, then the base is obviously A, and the bound is also to that. All of this is done at the programming language level. Then all the access to A0 to A511, they will be allowed. But if you go beyond that, we just stop that at runtime. Okay, very, very simple idea, right? The problem of this is very expensive. Every pointer you have, we need to create another pointer, a bound for it. And also all of this access you have here, you are going to check. You need to check if that access is allowed. Let's say, or if you assign a pointer to another pointer, the same thing happens. You need to propagate what happens, right? So this can be very, very expensive. So at least 2 times overhead on storing a pointer tool overhead on the assignment, because you need to assign the original pointer and also the bound. And also when you do every access, you need to add some comparisons, right? So this is very expensive. Good in theory, not necessarily adopt in real world. There has been some papers talking about that. There is a programming language paper, PLDI paper, 15 years ago, 17 years ago, using pure software solution to do that. There is also a hardware solution. They changed the CPU to do that, but still, it's still very expensive. So that's why we do not use them very often. Another approach, this is a widely used approach, is data execution prevention. Sometimes it's called DEP, sometimes it's called write or execute. It means that memory region, as long as it's writable, it should not be executable. Okay, very simple idea. Some other feature just called NX, not executable. Okay. Let's see what this stops. We want to pull off what we did just now. We need to put the share code onto a stack, and also the stack must be executable. Right? So this approach basically takes out the second condition. You still have the ability to put the share code onto the stack, but the stack will not be executable. You're trying to execute something on stack, you get a segmentation fault. Okay. Basically the MMU, memory management unit, will tell the program this memory region is not executable. That's it. The idea actually comes from some very old school. I think in the computer architecture class, you probably learned the Harvard architecture and also the von Neumann architecture. In the Harvard architecture, we store instructions and data in separate memory units or separate memory regions. We separate it separately. But most of our computers at hardware level, we're using von Neumann architecture, which this is the main memory. At the main memory, we store code, we store data together. Okay. Some architecture, they separate this at the hardware layer. Some microcontrollers, they will specify this physical memory region is only for code. This memory region is only for data. You cannot put code there. Okay. But with the help of memory management unit, we can do something similar. We can separate it. Okay. So old CPUs, especially before 2000, they do not have the permission of executable there. They only have readable permission and writable permission. And the readable implies executable. Okay. Then 2003, AMD 64, they introduced that NX bits in the memory management unit page tables to indicate this memory region is not executable. Windows started to support that from Windows XP. Because this is a CPU support feature, the OS needs to implement that. The Linux also started supporting that in 2.6.8. So now when we compile a program, we want the executable to be, the stack to be not executable. We can explicitly specify this option to GCC or LLVM, whatever compiler you're using. Or in most cases, right now it's by default, it's not executable. Okay. The reason the programs right now is the challenges you have been hacking so far, it is executable is because I gave a different option to make it executable. By default, it should not be executable. Okay. So let's say one program, Overflow 6, we just saw that. Overflow. Overflow 6, 32-bit. So we can use readelf L to do that. Readelf L. Buffer Overflow 6. As you can see here, do we find a stack somewhere? stack. Okay. So stack is at, so this is the version that you guys, did you guys hack this one, Overflow 6? Not yet? Okay. Oh, wait, this is what we're working on. So you can see this memory region, this stack is readable, writable, and executable. Okay. Which means you can inject the shellcode on stack, it will be executable. Another version of this it's not executable. This one. You can see stack is readable, writable, but not executable. Okay. But this is just an application. So what happens is this is the header of that L file, right? So what happens is when you try to run this program, you are launching this program, the OS will load this program into memory, right? The OS will configure all the memory regions for this application using memory management unit, MMU config page tables. That's what we learn in computing system class, right? There, the OS will read the ELF header to say, oh, this program is asking the stack to be not executable. Okay? Then it will mark at the page table, this memory region is not executable. Or the OS says the header, it is asking this header to be executable, then it will make it executable. That's it. So eventually, OS is the enforcer of this policy. So here it's more like, oh, we're telling OS what we want to do. So what DEP cannot prevent, you can still corrupt the stack. Okay? You can still put the shellcode there, or you can overwrite the variables on stack. You just cannot execute code there. You can also obviously crop data on the heap, but we haven't talked about heap yet. That's something we will cover the second half of the class. And you can still overwrite the return address in this case, right? It doesn't stop you from overwriting the return address. It only stops you to execute code on stack, okay? So what if you overwrite the return address to point to some legit code section, just code that already exists? Have we done something like that?
Return to print flag or print secret.
Yes, we actually have done that a lot, right? The very first challenge we did, we returned to print secret, right? Also, there are F1, F2, I asked you guys to chain them together. So those are legit functions in the address space. We can still return to them. What other interesting functions are there we can return to? Those functions are what I placed there. Exactly, there are all kinds of C library functions. Okay, that's why there is an attack called a return to libc attack. Okay, and we will talk about the 32-bit version of that. That will defeat this kind of DEP here. So this was first discovered by a hacker named Solar Designer back in 1997. The idea is very simple. We overwrite the return address. Then we return to a C library function, a very powerful C library function. All of you already know how to do that because we have been returning to a function I placed there. It is the same technique. You only need to find out the address of those functions. That's it. Also, the parameters, right? For example, the C function has C library has a function called system, and the input is a string. It will execute that string as a count. Okay? For example, if you want to get a shell, you can do /bin shell, and it will create a new process for you. Under the hood, it will use that execve system call to do that, which means we will be able to do this on our system. However, it will not give us a root shell. It will be a long root one. Because when we create a new process, this Linux version we're running our server will downgrade your permission. To make sure it doesn't downgrade that, what we do? We do a set EUID thing. That's a system call. But is there something else we can do here? Who said that we have to run this command? Oh, yeah, even other command will be the same thing. Okay, but still, let's show that. Let me show you guys how to do that. Okay, so we're going to use Overflow return 4, which is a challenge you are already familiar with. But this one is different from the previous one. The stack is not executable. Okay. Everything else is the same. The code is the same. Let's find that one. Overflow return 4. We have many different versions of this to add all kinds of security features. You can see there's a cookie one. Going to defeat the cookie. This one. This is a program. Let's do a check sec on this. Oops. Okay. Do a check sec on this. There is no stack Canary, but long executable stack is enabled. Which means even if you inject your shortcode, you will not be able to run that. Then the program is the same as before. You have a buffer, 30 bytes at a C code level. You have gets. You have then return 0. That's it. You can overflow the return address, but you cannot inject the shellcode. You can inject the shellcode. You cannot really execute that shellcode. So we need another approach here. The approach we want to use is we want to return to a C library function called system. Let's see how do we do that. The first thing is we need to find out where is system. An easy way to do that is we just debug this program. When we debug this program, we run this program, then we just use p print to, we need to run this first. We just run this program. After we run this program, C library is loaded. Before we run the program, C library is not loaded. That's why when I do p system, it doesn't give me anything. Then I run this program, use R, then I just do a p system, and it tells me the C library system function is at this address. Okay? So we know where the C function is. What else do we need?
The system function like necessary for all programs? Is it loaded for all programs?
By default, yes. So although all C programs, by default, they will load C library functions. And actually, they share the same version of libc. Yeah. But there's another issue is we talked about at the first class is the late binding issue. So this address is not necessarily the system function's address. It could be a stop address, but that doesn't really matter. Even if you call a stop, you should get the same thing. Yeah. Okay. So now we know our return address. What else do we need? If we just return to system, we don't get anything, right? Yes, parameter. What parameters? What is the parameter for this one? It's a string, right? So how do we find a string? We can inject one in environment variable, okay? But maybe we can just find one, I think. What we're looking for is, how do I use find again? DB command to find something in memory. Find, okay, start address, end address, value. Okay, that's it. Okay. We also need the module. So info, give us modules. Remember, it's info module. Info module function, info module. So what I'm trying to do is just to find that string /bin/sh in the memory address, because the C library actually already loaded somehow. I don't remember why they loaded, but the string is already there. So we're trying to find from the C library. So we need to find the C library's address. Okay. DB command to view modules. Info sh. sh. Okay, so we have libraries loaded here. So this is a libc, and also the interpreter, the loader. So libc is at this address. See, so then from those addresses, let's find the string. Here. I'm not sure this is the correct syntax, but let's try. The syntax. You guys, oh, there is a comma there, another comma. Okay. This reference. Oh, we do not really find a string there. We'll find just a sh. Nope, I don't find one. Let's search for maybe this address. Seven, 3, switch. Nope. Where else we can find one? What did you say before?
Might be including that search.
Oh, that's a good point. No, seems single quotes, double quotes, does that matter? No. Okay. Let's see. What other regions we can look for this? It happened. We found this before. Let's see. Of course, we can always go back to the environment variable approach, but let's see. Let me check. You guys can also try here. Try to find a string.
Right?
It's more likely be in the libc section. We can search other sections as well. DB commands to list or modules. The library, oh, files, info files. That's what I'm looking for. Info files, let's say. Let's see what other regions we may find that. Read-only data, we can try there. That will be the read-only data for this executable, so probably not there. Let's see. Only if this doesn't work, we just go back to environment variable. Where's nope, do not find one.
Is there a reason we can't just check the whole space?
I think it will trigger a problem. We can try.
I'm reading that it just tries it. So
No, see? So if that memory region is not mapped, it will stop there. Yeah. Okay.
On
let's-
the way there.
yeah, I got it.
Yeah.
Where?
So I did the find that you did before, but
Yeah.
I included all the memory in the two libraries that appeared when we did the info stage. Like from F7DE71D0
Okay.
all the way to F7FE
Okay.
F893.
Oh, okay. So basically a little bit bigger than that. So F7 DE or you don't have
I did DE
okay.
D1 D0
Okay.
to F7 FE F893.
FE F8. Okay. Let's look at that. Oh, that's too big.
Just one.
Where?
The bottom.
Oh, it's here. Okay. Yes, we do find one. So let's examine that. So how do we examine that? We use X exam. Exactly, here's S, right? S here means string here. Then we just examine that address. Are you sure?
Yeah, but I think the
Sorry, I should not dereference that. That's right. Okay. Yeah. I dereferenced it. That's a start. We should not use a start. So okay, we do find a string there. Okay. So it's already in the address space, which we can use. We find that address. Let me copy that. That's the address of the string. We also have the address of system, which is here. So now we go back to how big is our, we need to check how big is our buffer there. Our buffer is at EBP minus 30 in hex, which is 48 bytes. So, okay. Buffer, this is saved EBP. This is return address. This one is 48 bytes. This one doesn't matter, garbage, 4 bytes. Return address, we will change this to system's address. Then we need another 4 bytes of garbage, right? Do you guys remember that? Another 4 bytes of garbage. Then we need the first parameter. What is this one? The address of that string, right? So the address of just the bin sh. Okay. So if we get that, we should be able to get a shell, even though it will not be a privileged one, but it should give us a shell. Okay, so this one takes input from std in, so we need to pipe it in. So 52 bytes of garbage first, then return address, which is F7, E0, F7, 80. Well, after that, we have another 4 bytes of garbage. Then we have 4 bytes of the address of the string, which is saved here. F7, F5, 63, 63. Okay. We'll probably need a cat to make sure the file descriptor will be open after this. So we'll type this into the program. See if it works. Okay. I don't know yet. Yeah, it works. We get a shell. Okay. Why? But it's a CTF shell. Okay. So it's not a root. Okay. So this is basically return to libc. You can execute whatever commands there, obviously. Instead of doing a bin share, you can also execute command cat flag. But where does that give you the flag?
Maybe because the program's running as the root.
No, because when you do that, it's creating a new program. And that new program will execute cat. So it's already downgraded its privilege. So you won't be able to get that.
It's not like setUID.
No. So for the same reason, you cannot do a change mod. It will not also. It will not work either. Yeah. You mean here? Oh, that's a good point. But does that matter? Doesn't really matter, right? So here, how many more bytes I'm giving here actually? These are 2 bytes. This is not hex value. This is ASCII F, 1 byte. This is ASCII 5. So it doesn't really matter because we only needed the first 4 bytes. So without that or with that, doesn't really matter. Let's try. Right? Doesn't really matter. Or you just put a ton of garbage there. Doesn't really matter. We're not using that. Okay. Make sense?
So could you repeat how we found the address for bin.sh?
So bin.sh is already in the address space. It's part of libc. In GDB, we use that found command to look for that whole memory region to look for that string. Yeah. Use a bigger memory range. So the reason I didn't find it in the first place was also we were searching a very small memory region there. Yeah. And also, you can just put that in environment variable. Yeah. So that is basically return to libc. But we actually already learned this in the second class. We just didn't return to libc function, but it's the same principle. You can return to any function. The generic version of return to libc is to not. Yeah, go ahead.
Can we get a root shell by this method? Like, can it really begins? Add anything else?
Not return to system function. There are ways to do that, which, for example, you use a more generic version. So you see, the return to libc, you are trying to return to a real function, right? That function could be a libc function, could be a function I placed there. You are returning to a full function. But why do you have to return to a full function? You can return to some gadgets, several instructions that end with a return instruction. Okay? So those gadgets usually are small, 2, 3, 5 instructions, and always end with a return instruction. And those gadgets are not necessarily emitted by the compiler. Let's say you have an instruction move some data to EAX to EBX. But if you interpret that instruction from the middle, it becomes an instruction, then a return instruction. Make sense? Because the Intel instruction set, those instructions, they are variable lengths. We have seen some instructions with 1 byte, some instructions 5 bytes. So there are instructions 10 bytes or I believe 12 bytes. Okay, which means that 12 bytes instruction, if you interpret it at the very beginning, it will be a 12 bytes instruction. If you interpret it from the second byte, it may be 3 valid instructions. So those are not really emitted by the compiler, right? But they exist. Then you find all kinds of gadgets that the compiler didn't intentionally created in the address space. And with that return instruction at the end, you chain them together, you can do whatever you want. You can do, you can pick your privilege of the root, basically. So that is called return-oriented programming. That's a more generic version of return to libc. And that's what we're going to talk in the second half of the class. Yeah. Okay, so here, let's say, so what we have done so far in the last 2 classes is to hijacking the control flow. If for all the instructions, if those instructions are not control flow instructions, then you just execute one instruction after one instruction. Go to the next one, right? But some of the instructions will have a jump, have a core. They will change the control flow to other places, then, or sometimes may come back. So this kind of attack is called the control flow hijacking attack. Usually it exploits a memory corruption vulnerability, like we said, we saw there. And usually we will overwrite a code pointer somewhere. Sometimes directly a code pointer like return, sometimes not directly like the saved EBP, because that point to a structure which has a code pointer, the return, right? One way to defeat this is the general approach. We're not talking about that today. It's called control flow integrity, which our lab actually do a lot of research on. Then one type of this code control flow hijacking attack is very specific. It's where we inject the code, right? That's why that is called the code injection attack. What you did last class and also early this class. So this is a subclass of control flow hijacking attack, and the code share code needs to be supplied by the attacker, and the share code, they are just the machine code. They are instructions, which means if you are attacking different architectures, the share code will be different. Even if it's the same CPU architecture, your share code may be different for different OS, because you are trying to make system calls, right? On Windows, on Linux, the system call numbers are different. So that's why the share code will be different for different architectures. Another class of attack, like the return to libc, is called the code reuse attack. This is also a control flow attack, but you do not inject the share code there. What I showed you just now, return to libc, or what I talked about just now, the return-oriented program, you are reusing code already in the address space, like the system function, like the print secret function, or even not full function, just several instructions under with return or other instructions. Those are called gadgets. Okay. There are return to libc, return-oriented programming. We're going to say that second half. There is also jump-oriented programming. However, on Linux, jump-oriented programming is not very easy. We do not see many gadgets for jump. So in this class, we focus on return. So let's revisit this part. Attacker's goal is to take full control of a victim's machine. It will hijack the execution flow of a running program, eventually execute arbitrary code. This can be done remotely by taking input from network. That's called RCE, remote code execution. So they change the control flow by modify some code pointers, return address, function address, those things. There are many different types of code pointers. There are code pointers on stack. You already saw that. The return address, the stack fragment pointer, EBP, also eventually points to return address. In C, we also have this long jump, set jump mechanism that will also save pointers. Okay. Also, in the OS class, we started interrupt. The interrupt will also save pointers in memory. Also, in C++, we have, or other object-oriented programming, we have inheritance. How do we achieve inheritance? We have code pointers. So we use the same interface to call different functions, right? We use the same interface to do that. Because underlying, they have different addresses, even though we are using the same interface. And those functions in C++, they are stored in something called a virtual table. It is at the beginning of an object. There is a C object, a class, right? Then in memory, at the beginning, there is a virtual table. That virtual table points to, have many code pointers. Those are the code point functions for those methods. So there are many function pointers. If you override those, you can also hijack the control flow. Even the example we saw before, like let's say log here. Okay, well, we will get there. We saw that there is a challenge for that. Let's say I talked about this before. There are many different pointers, code pointers, data pointers. We can skip this to focus on actual text. Okay. The second defense, which is also widely deployed right now by this is a compiler feature. This is called a shadow stack approach. The idea of this is actually quite simple. The ability of the attacker here is to overwrite the stack, right? And the return address is on stack. So what if we have 2 copies of the stack? We do not need to put everything on 2 copies of stack. We just put the important things, like the return address. Okay. We put a return address at a different location. And when we return, we do not use the return address on the main stack. Instead, we use a return address at another additional stack, which we call a shadow stack. And there are many different ways to implement this. Let's say something called a traditional shadow stack. This is one way to implement that. So we can use one register on x86. We can use one register GS to store where our shadow stack is. So here we have 4 function calls. We have R1, no. We have, we have R1, R0 to R3. Those are 4 functions. One calls another. So their stack will look like this. They will go down, right? So on the stack, we will have parameters, we have a return address, we have saved EBP, we have local variables, right? That's for one function. Then the R2 calls R3, then R3 will keep generating those kind of data, right? Parameters, return address, save the EBP, local variables. And the return address is stored there. We already know that. So in addition to the main stack, we store another copy of all the return addresses at a different place. So the assumption here is even if the attackers can override here, like what we did, they will not be able to override here Okay, but this assumption is not very strong. If the attacker has the ability to override here, maybe he also have the ability to override here. But still, make it slightly harder. Another approach is called a parallel shadow stack. The basic same idea, except that there is a fixed distance between the original saved copy of return address and the additional copy. Okay? The reason we do this is it will run faster, even though we are going to waste a lot of space. This approach, we're not wasting space, but this approach, we're wasting space, but run much faster. I will show you some code to say why it is that case. Let's say figure 2 here. I took both figures from just a paper. That's why they are using AT&T syntax here. Let's say the figure 2, that is that's the beginning of the function. So that's the prologue of the function. At the beginning of the function, we have what? Push EBP, move EBP to ESP, those kind of operations, right? In addition to that, we have those operations. So the compiler will automatically generate those instructions at the prologue. So this can be transparent to the software developers. C code writers do not need to care about this. Let's say GS 108. GS is a general register. This is to indicate where our shadow stack is. Let's say there is a variable in the memory, and we think that variable is a pointer. That is our shadow stack pointer. We call it SSP. Okay. So we subtract 4 to that, which means we're going to push something. Okay. So here we are simulating a stack. We cannot use the real push instruction to do that. If we use a real push instruction, to go to the main stack. Right? Then from there, we just move this address to EAX. Then we copy the return address. Where is the return address at the prologue function? Where ESP points to, right? So we just copy whatever ESP points to, right? We move that to the register ECX, okay? Then we move whatever ECX to where EAX points to. Okay? So we're basically copying the return address from the main stack to another stack. That's it, the 2 copies. That's the prologue. So at the end of the function, at the epilogue, we need to check whether they are the same, or we trust the shadow stack data more than we just directly use the shadow stack data. Right? But let's say what we do. We move this pointer to ECX. We add that, which simulates a pop operation. Then we just move whatever ECX points to, that's our shadow stack, to EDX. Then we just move whatever EDX has to what ESP points to. Okay, so this code here is not trying to compare. This code is trying to use whatever we have in shadow stack to overwrite whatever we have in main stack. Okay, so even if there is a hijacking, there is an overwrite to the main stack's return address, we will be able to fix that. Okay, but this is not a perfect solution because you can see that you can still override EBP, and this one doesn't protect that. Okay. So this is one way to do that. Of course, instead of just fixing that or using that, you can also compare. So here is another example. We compare what EDX has and what ESP points to. If they do not match, means some overwrite has happened. Okay, either in the shadow stack or the main stack. Either way, there is an attacker. Then we just abort. Right? So that's another way to do that. The overhead here, you can see there are several more instructions, several memory moves. We are moving from main stack to shadow stack or shadow stack to main stack. There's a compare, there's a conditional jump, and those are the overhead for each function. So for each function you want to use, you need those. Okay. So modern compilers like LLVM, I don't remember if GCC supports shadow stack, but LLVM definitely supports shadow stack. There is an option to add a shadow stack there. Another approach is a parallel shadow stack. This one will be a little bit faster. Okay. The assumption here is there is a fixed distance between the return address at the main stack and the return address at the shadow stack. Then to save, we just need one instruction. We just pop ESP to a fixed address. So this is a fixed number. It points to a memory region. So this pop instruction actually can do memory to memory copy. Okay, just that. 2 instructions. We can do this much faster than before. Then the epilogue is the same. You just add, then you do a push. Okay, that's why this one will be much faster. Just one memory copy using the push or pop instruction to do that. So the overhead, some analysis showed measurements show that traditional shadow stack almost 10% overhead for each function. But obviously, it depends on how complicated your function is. If your function is super long, the overhead will be small. But you also do not necessarily want to have super long functions. You want to modularize your code, right? Then for parallel shadow stack, the overhead is smaller, 3%. That's the second difference. The third difference is also widely deployed, and we're going to defeat this today. It's called stack cookies or stack canaries. This can defeat sequential overflow, what we studied so far. The paper was originally published in 1998. Has been 28 years. The paper title is Stack Guard, Automatic Adaptive Detection and Prevention of Buffer Overflow. Okay. The idea behind this paper is super simple. Okay. The title sounds a little bit fancy, but super simple idea. This is deployed in all of your devices right now. Even in the kernel level, this is deployed. Like when you compile your code, say code, compile kernel, by default, they will generate this. Okay. Super simple idea, can be defeated, but it's just computationally so affordable. That's why it's widely deployed. It actually received a Test of Time paper award many years later, maybe 15 years later. Yeah, because it's so widely deployed. This is a compiler technique. It's done automatically at a compiler level. So C code programmers don't need to do anything. Okay. This is trying to, you don't need to change source code. This is going to patch the function prologue and epilogue. Same as what we saw for the shadow stack one. They also change the epilogue and prologue. But that one is a little bit more complicated than this one. In the prologue, we are going to push an additional value on the stack. We call it a Canary. Okay, Canary is a cat, right? A cat you bring to mines, and if the cat is dead, the miners know something is bad, so they go up. Okay, so here we put a Canary there. Then in the epilogue, we just check if the Canary value has been changed. If it has been changed, it means there has been an overflow. Okay, we do not directly check the return address. We do not directly check the saved EBP. We put a random value of the Canary there. We check that value. Okay. If that value is changed, we know there has been a sequential overwrite. But if your overwrite is non-sequential, which I will show you example, you can skip that one. So there are also other ways to defeat. So we use the same example here, overflow return 4, which is, you are already very familiar with this. Okay, we just hacked one version of this. So the left-hand side is the binary code, the disassembly code without Canary of Volfu. We have ndbr32, which is also a security feature. We're not really using that right now. So we have push EBP, move ESP to EBP, subtract something, load the effective address of buffer, push EX, call that. Which function was that? String copy. Get. Yeah, we call gets. Then we add, we move, we leave, we return. That's it. Okay. So you're already familiar with this. The cookie version, Canary version, is on the right-hand side. A little bit more complicated, but but still very simple. The new additions here are those 3 instructions. I know there are some other additions, but they're not necessarily related to this. That __ x86 dot get pc thunk.ax, that is related to position independent code. Okay, so we will talk about that when we talk about address space layout randomization. So we ignore that for now. So what we really added here are those 7 instructions for Canary. Okay, the first instruction is we are moving some data, 4 bytes of data from another memory location to ECX. And that memory location is identified by the general register GS with an offset. But we're moving 4 bytes from memory, okay? So that 4 bytes are the Canary. And when you launch the program, the OS, or let's say the loader, will put 4 bytes of data, random data there for you, for the program, and that data is the Canary. So whenever you launch the program, it will generate a new Canary, okay? During the lifetime of this program running, it will use the same Canary, okay? So that's the current implementation. You can say it would not be that secure. For many server applications, it runs forever. So even if you have a Canary, they never change. If you figure out once, only 4 bytes, then you figure out everything. We move that Canary to ECX. Then the second instruction here is we move that ECX to EBP minus C. Okay? That's it. We're putting that Canary onto stack at EBP minus C. Then we just exclusive OR ECX, clear that to 0. Then our buffer is at EBP minus 34. Previously, our buffer was at EBP minus 30. Now EBP minus 34. So if we think about the stack, what do we have? Probably that one. So let's see, what do we have here? We have EBP minus C. This is our cookie or Canary. Just call it cookie here. Then obviously above that, we have EBP points to saved EBP, right? So this is C, which means this is 12 bytes. Then here we have our buffer. At buffer now we have EBP minus 34 in this case. So in this version, our buffer is actually smaller than before because the cookie is here. You cannot write to a cookie. Make sense? Yeah. Then after this function executes, at the end, we are going to move that EBP minus C, that Canary on stack, to register ECX. Then we compare whatever in this ECX with another place we store the Canary. Okay? The GS14, that is another memory location where we store the Canary. We exclusive OR them, so basically the same as compare. Right? Then if they are equal, we keep going. Otherwise, it will call another function, part of the libc, which is called _ stack check fail local. That's it. Okay, that's a libc function, and that function will print out stack overflow detected something. Let's try that. This is a cookie version. Cookie. So this takes input from. Oh, should be much bigger. Maybe enough data there. Yeah. Thanks. It print out stack smashing detected, terminated, aborted. Okay. So it was not any of my function to print out that. That's a libc function because it detects that stack overflow there. We can debug this. GDB. They're involveful, right? This is involveful. We just run this. Then we are going to, oh, we should set a breakpoint after gets. Oh, maybe before and after gets. So this is a breakpoint after before gets. We continue here. Then we examine the stack. We examine, let's see, 4 bytes from EBP minus C. What is EBP minus C again? The cookie, right? We examine there. Oops. See hex value. So these 4 bytes, they are the cookie. 37, 94, 15, 00. This is random value. Okay. On this machine, on this Linux, the last one is always 0. Okay. So actually there are only 3 bytes of randomness here in this case. Then those bytes don't really matter. 8 bytes don't really matter. Then after that will be the saved. This one is saved EBP. This one is return address. We have it. Now, we do need to set a breakpoint there. Set a breakpoint at this address. Oh, we don't. We just do a line there. Then it's asked for our input. Just input a lot. Overflow that. Then we examine this stack again. We overflowed everything, right? The stack Canary, we overflowed with F, which is 66. And we also overflowed everything else. Then we keep going. Okay. We are here. We are going to load the Canary and compare the Canary with this value. One, two. Okay, we're going to compare. After compare, we're going to jump. So we know they are not equal. So we should not take the jump here, right? Instead, we should call this stack check fail function. If we do an I here, we should be here, right? They compare that Canary value, and they are not equal. So we are going to call the state library function fail local there. That's why that function will print out stack smashing detected. Yeah, that's it. Very simple idea. So that GS, if you are not familiar with that, we actually talked about that before. That is a very old register, has been there for decades, but we do not usually use them. Previously, they have different purposes, especially at the era of segmentation before paging. We use those registers a lot. So this is code segment, stack segment, data segment. E is probably, not sure about what do they call that, but those are different segments. But now we have MMU, we have paging, we don't really use them that often, or we use them for different purposes. And GSFS are not really used for the same purpose as CS or SS. So GS is a register we use for store something we call thread local storage, I believe. So the Canary here, very simple idea. We just put some data there, random data, technically only 3 bytes. The last byte is always 0 in this implementation. The 64 byte is the same thing. Instead of using GS, they use FS. Then the same idea for everything else. You move from a global variable, which is for the Canary, then you move that to stack. The 64-bit version, you move to RBP minus 8. Then when your function returns, you check if that value is not modified. That's it. Okay. Same idea. The overhead, you can say probably 7 more instructions, 7, 8 more instructions. Some memory moves there, one conditional jump, some compare. So it's not too bad. Okay. The overhead is not too bad. The GSFS, especially for those 2 offsets, they are for something called thread local storage, TLS. Each thread will have a storage, and that Canary is actually stored there. And the Canary is generated when that program is launched and stored there. There has been some discussions about what we can put in Canary. What we saw and what is usually implemented is just a random value. Also, some people say you can put some other values, just like all zeros there, or you can put terminator canaries like return those things to basically to defeat string copy those things. But they're not super useful. So how do we? Oh, so this figure is actually from a paper we submitted, was published. We talked about how Linux handles Canary and how embedded systems handles Canary. And our argument is for most embedded systems, those microcontroller-based systems, even if they have a Canary, it actually doesn't do anything. The reason is those systems, they do not really have the concept of process. So the Canary is generated when that microcontroller boots, and the microcontroller may stay there running forever. And there are many ways for you to extract Canary from embedded systems. They never get changed. For applications, at least every time you run it will be different. Forgot to show you guys that. Let's say that. So let's say we run this again, and we examine the Canary again. This Canary. DEP minus C. So should it be where? Where are we? Oh, wait, it should be. So right now we haven't set up EBP. That's why. A little bit lower. Good. Now we already set up the EBP. Oh, we haven't set up Canary. Sorry about that. So we need to, let's stay here. This address would be better. Okay, so this is where we already set up the Canary. We continue, we examine this. You can see, now we have a Canary 74 1F 8B00. This is different from what we saw previously, right? So let's run this program again. Start from beginning. I think we should hit break 3, then 4 maybe. So we run the program again with run. Now it has a different Canary, C6 DD3700. Different. Every time you run the program, OS will generate a new random value for you for your Canary. If you are interested in how this works, I paste the link of the code for Linux here, and also libc here. You can read the code to understand how this is actually implemented. A little bit of history of that. The paper was published in 1998. The authors of that paper, they implemented this in GCC. So they had a patch to GCC. Then IBM developed something called ProPerlice. I will show you later. It will place buffers after local pointers in the stack. So all the code you have seen so far, the local variables, the first appeared local variable will have a higher address. The second appeared will go to a lower address, right? That's why in the very first example, we have a local variable I, then we have a buffer, then the buffer can overwrite that local variable I, remember? Right. So IBM introduced this called properties. They are going to reorder those local variables. Even at the straight code level, you have I first, then buffer. They are going to place buffer at a higher address, then I had a lower address. Then they will place a canary there, which means you cannot overwrite the I, even if you can overwrite the canary. Google also implement the fstack protector strong flag for GCC and also LLVM to add canary for almost all functions. And also Ubuntu, they are compiled with a stack protector since 6.10. Arch Linux was compiled with this flag as well, 2011. And even after 2014, all packages on Arch Linux use stack protector strong, which means every function will have canary. Okay. So this is a figure of the ProPerlice. We have 4 local variables, A, B, C, D. A typical implementation of this is A will have a higher address, then we have B, then we have C, and we have D. Right? Then the IBM ProPerlice implementation will reorder those local variables. They will place those buffers, C and D, at a higher address, then A and B at a lower address. Then even if you override D, you can override C, but you will not be able to override A and B. C can override canary, obviously, but not able to override A and B. So that is a difference. How do we bypass this? Okay, this is a fun part. How do we bypass this? Okay, let's say. First of all, you can bypass this if you can find a bug for an arbitrary memory read. There is a bug to allow you to read anywhere in the address space. Then you will be able to find the canary value, right? The canary value will not be updated, will not be changed during the lifetime of that process. Okay. Or you can just brute force. But we have in 32-bit version, we have 4 bytes of canary, 1 byte we know it's 0, which means the other 3 bytes, still there are 60 millions of combinations. 4 bytes in total will be 4 billion. 3 bytes will be 16 million. Still a lot. Okay. So every time you attack a program, it will have a new canary. If you just randomly guess, you have 1 out of 16 million. That's a probability for you to succeed there. Not very high, right? However, there's another problem is the canary value will not be updated if the program is forked from another process. So, yeah.
So why were we seeing it change then? When we run the program, we're 4 bits from one.
Can you repeat that?
Like Overflow in the terminal, right?
Yeah.
We're forking from the so when we do that to create.
Yes. So exe CVE will change the canary, but a fork will not. So if your program only do fork or clone, doesn't do exe CVE, the canary will not be updated. Yes. There are many programs that will fork itself and don't do execve. For example, a web server, they will fork a lot of workers and do not necessarily do a execve to replace itself. Right? So for those programs, the child process will not have a new canary. Okay. Then in that case, we actually can guess the canary byte by byte instead of guessing all 3 bytes together. Okay. We try to overwrite the first byte of the canary. If it's not successful, we keep trying, and it takes at most 256 times for us to figure out the first byte, right? We didn't touch other bytes, right? After we know the first byte, we start guessing the second byte, take another 256 times. So technically 700 times, we will be able to guess that. So that's what we're going to do with this program. This is the program we're going to hack. The idea of this program is to simulate some kind of web service or whatever. It has a main function, which has a big while loop. In the while loop, it will fork itself. In the child process, it will print out the process ID of the child process. Then the child process will call the vulnerable function val_foo. Then it will call iptd the foo. Then it will just exit. Okay. In the parent process, it doesn't do much. It print out the parent ID. Then it will wait for the child process. Okay. So if the child process exits, then the parent process will keep executing, right? So the parent process will go to the top of the while again. It will fork another child. That's it. So at any moment, there will be the parent process and the one child running. It will not be more than one child running at the same time. Make sense? Okay. The parent process doesn't do much. It will just monitor if the child is dead. If not, wait. Otherwise, fork the child again. The child will call val_foo. That's it. Val_foo has a buffer, 40 bytes. And this program is compiled with Canary. Okay? Has a buffer, has a local variable, file pointer, then it has a big loop as well. The big loop is trying to open a local file, take input from the local file. Okay? We'll simulate some kind of input. So obviously this can also be network input. It will try to open that file. If that file doesn't exist, it will just break and keep looping there. Okay, look for a file. Which means as an attacker, your job is to create that file and give your input in that file. Then this child will read that. From there, it's going to do a memory set of the global buffer, which is 200 bytes. There's a global buffer. So you can see there's no bug here. Okay? The global buffer is 200 bytes. We're memory setting 200 bytes. The buffer there. Then we're going to read from the open file temp exploit 70 bytes to the local buffer. Okay. So that is probably where the problem is, because we're asking for 40 bytes, but it's reading 70 bytes. So maybe that will overflow things, right? Then it will also print out the child read how many bytes and what is the guessed canary there. You use this to figure out where the canary is. Okay. So after that, so this f-read actually no bug, because this f-read we're reading to the global buffer. But after that, we're going to copy from the global buffer to the local buffer. That memory copy is where the bug is. So no matter how many bytes you put there, it will copy that. Then it will close the file and remove the file. Okay. So that is the child process. Any questions here? We run this program. So 2-bit. We probably need 2 terminals for this. Max. 2 terminal would make it easier. Okay. We have this program running. It has the parent process PID 56, child process PID 57. The parent process is waiting for the child process. The child process is waiting for that file to read data. That's it. So if we try to create a data on the right-hand side, we just echo blah, 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 blah. To hump, exploit. Okay. We created that temp exploit file, and the child process will read that file. The child process read 10 bytes from that file because I only give 10 bytes there, and we didn't really guess any Canary. We haven't even write to the Canary variable, right? Area, because our input is so short. Then the child process will print out IP to the full and quit. Then the parent create a new child process. That's it. So if we have a longer input, only used to be 16 or 70 bytes, get a little bit larger. Okay. So when we do this, we successfully overwrite the Canary. Those are the 4 bytes we provided there. So I think this 3 is actually hex value 3. So 3 actually has an ASCII value of 33? I think so. ASCII table. Oh, 3 is actually 33. That's why it looks a little bit confusing there. You see a lot of 3 there, but okay. So let's try a different one. That looks a bit confusing there. Let's put all A's here. It should be, what is ASCII value for A? A is 61. So we guessed the Canary value. We put 461 there. And obviously, that's not the correct Canary value. I don't know what is a correct Canary value right now, right? I just run the program. It's a random value. No one knows. And smash, stack, detected, terminated, put another process, child process. Okay. So our goal is to guess this one by one. So we guess the lowest byte is always the highest byte, or the lowest byte is 0. The lowest byte is 0. And we are guessing, we're writing from buffer, which we're writing from a low address to a high address, which means 1 byte will be 0 there, right? So the idea of this is simple. The buffer, by disassemble this program, we will know that the buffer is at EBP minus 34, which is EBP 34 in hex, which is EBP minus 52. Okay? Then the Canary is at EBP minus C, which means the buffer is 40 bytes. Second level, we ask for 30 bytes. compiler actually gave us 40 bytes here. Okay. Then the Canary, we know the last byte is the least significant byte is 0. Okay. Our goal is we overwrite 0, 0 here. Then we overwrite 1 byte from 0 to 1. Right? If it's successful, we do not touch the other 2. Okay? We only overwrite that. So if it's the same, eventually in 256 twice, we will find 1, which is correct. Right? If that is correct, we didn't touch those 2. 0 is correct, which means the Canary is correct. So it's not going to print out stack, smash, and detected. It will not print out that, right? It will print out what? IPD the full. Okay? So then we will know that byte. Then we move forward to the third byte, do the same thing. If we successfully guess that, it will give us IPD the full, right? Then eventually we find all of them. Then we can override everything here. And this one, we only have Canary, but we don't have, remember, we don't have, let's see. Let's forget about that. We have Canary, but we do not have non-executable stack, which means we can have share code there. Okay, so let's put the share code there first. So eventually, when we figure out all 4 bytes, then we just use those 4 bytes as Canary. We overwrite the return address, which go back to our share code. We can get the flag. Right? So that's the idea. So I have a script for that. It's a very simple script. Next week, it's your homework to write a much more better script. You can use Pound tools to do that, or you can just change my script. The goal is to write a fully automated script. My script is semi-automated. I will show you later. I'm going to add this little by little. Okay. We're going to show a semi-automated demo here. Your homework next week will be write a fully automated. So let's first create a we inject the share code there first. Bigger. So now we are in box. We get that share code there first. We find the address of the share code. So Week-4 somewhere there. Then another terminal. Let me make sure the share code is also for this terminal. It could be there. It's not there. Oh, this terminal doesn't really need the share code anyway. Yeah, this terminal doesn't really need the share code. Because this terminal, we're going to run our script to run to the file. So the terminal, the server program will be run on the left terminal. But still, we should be able to get them here. Let's see. Let's try to do it here first. It's here, rows tmux. So it's okay. See if it's there. Did you export? Okay, now it's there. Good. So this side should also have that, even though we don't really use it this side. Yeah, cool. Okay. So both terminal have the share code there, same address, which is good. Now we are going to write that script. This is our script. Going to run this at the right hand side. Just do this. We need to go to temp. Okay, so that's our script. Let's say we import from here. We define this. Oops. For file sleep. Good. This one should be which layer? This one should be the same layer as while. Here. Good. Then we also need to. Okay, let's say. Let's say this script probably too small. The script, we have a for loop from 0 to 255. We check if the current path, because we are in temp, so we're checking basically exploit file exists. If it doesn't, if it already exists, means the child process haven't been reading and deleting that. So we just sleep a little bit. Right, we'll go back. Then, if this file doesn't exist, we are going to create this file, and we are going to write 40 bytes of garbage there. Then we're going to pack C1. So this one probably should be updated, right? Not 40 bytes. How many bytes we need? How many bytes we need?
28.
No. It's correct. We need 40 bytes. Because this buffer is here, right? Buffer is at EBP minus 52. The canary is at EBP minus 12. So this is 40 bytes. Okay. But the least one will be 0, 0. So that doesn't really matter. After that, we can keep going. Yeah, I think that's it. So right hand side, we will be running this program. Let's see whether it runs. Left hand side, we can try to capture that file. Yeah, it's there. Okay, good. So that exploit is running. Then let's see what we do. On this side, we start the server. Okay. And because previously we have actually we run the script once, right? So we guess the what? We guess the 0 for the lowest byte, and it was successful because the lowest, least significant byte is always 0. That's why we do not have the stack overflow. Instead, we have pretty the full. Our guess is 0, right? So what we really want to do here is, so let's skip that part. We need to add 1 byte here. So here we actually need to add 1 byte. Okay. Makes sense? the lowest byte is always 0, so we hard code that one. Then we're going to guess the next byte, right? From 0 to 256. So now I'm going to run this program, and you need to pay attention here. One of them will show IPT the full. Everything else will show smashing step, right? So when you say IPT the full, you need to let me know there. Right? So we're guessing 0, 1, 2, 3 so far, or so this is a little bit low because of my weight there. So when you write your script, it can be faster. So, when we say IPT the full, then I'm going to stop the script and change the script a little bit by adding another byte there. So it read 42 bytes, 40 bytes of the buffer garbage, 2 bytes of Canary. That's why it's guessing 0, 0, 38 there. We have done maybe a quarter of them so far. Oh, we got it. See that? 57, right? So we go back to change our script. Seven. We run this again. Or we guess the third byte from 0 again. So your automated script obviously needs to read the input from this program. With pound tools, that's actually simple. I like it today. These numbers are small. What's that? 4A. We only need one more byte to guess. And 5. 4A. Oh, we're very lucky today. Those numbers are very small. Now we got it. 2 sticks. That's our Canary. Okay, what do we do now? We know the Canary. Yes, we just override the return address. How many bytes we need? Canary is 4 bytes. Canary is 4 bytes. Cookies 4 bytes. The whole thing is 12 bytes. So another 4 bytes of saved EBP. So we still need another 12 bytes of garbage. Then we have the return address, right? Okay, so we have another 12 bytes of garbage. Then we have our share code address, which we put there. D4C3, we have a lot of sled there, so let's just do D5. D5 probably too big. D5 for D5, not really. Not really. D5 DD. Okay, let's just do that. We run this again. This time we are sending our exploits. Yeah, we got it. Okay. Oh, we got the flag. And that side we'll keep sending. That's why everyone will get this. So that is how we can defeat. That's how we can defeat some kind of stack canaries for those fork programs. Okay. If it's not a fork program, every time it's regenerated, obviously it's a different story. It will be much harder than this. We still have like 50 minutes, so you can start working on the homework of this week. In particular, I want you to work on those 2 reverse engineering challenges. Yeah, 3 and 4. I will be. Any questions for today's class? The server program will look for that file. It doesn't really care if that file is changed. It will look for that file, read that file, then delete that file. Because the attacker script, the attacking script is generating the same thing. It's generating the same thing. The server, the child process of server, read that file, and it gets hacked. Then it deletes that file, right? Then the parent create another child, then we'll read that file again, get hacked, then keep doing that forever.